Alright, class. Unfortunately, I couldn't make it today. I'm teaching a class of my own over in Medway, so I'm recording this video so I can still at least teach you this theorem. There's the proof of this theorem. So I have theorem 3.6.3, and this pertains almost directly to theorem 3.6.1, which Brianna just presented. What this theorem states is, let P be a point in the plane inside our circle omega. Let TS be a chord whose midpoint is P, and let AB be any other chord containing P. Well, if you have all of those, if all that is true, then PT squared equals PA times PB. So let's just do some quick stuff to see why that is. So we're given that P is a point inside the circle, and TS is a chord, its midpoint is P. Everything in black there, that's going to be our hypothesis. So we assume that, as this diagram shows. So if we draw a couple extra lines, we can go ahead and get some triangles. So first, draw the lines connecting, the segments connecting AT and SB. And okay. So draw lines connecting, we'll just say draw lines AT and SB. So you'll notice this now gives us two triangles, PAT and PSB. So let's state a couple of things we know about these two triangles. So these two angles right here, APT and SPB, they're vertical angles. So we can conclude that those two angles are congruent. So we know these two angles are congruent. And we can write that down too. Note that angle APT and angle, I guess it would be BPS, are vertical angles and must be congruent. So if you will recall the similarity properties that I presented on Monday, one of them is just the angle-angle similarity. And that's probably going to be the easiest one for us to find. So we have one angle here. We know that this angle congruent to that angle, so now we just need two more angles that we know are also congruent. You can pick either pair of angles to do this with. I'll choose to just do A and S because they're on the top of our circle, the way we're looking at it. So let's draw a line. Let's just draw a little dashed line TB. Well, using Thales' theorem, actually I don't even think we need the line, but it just helps me visualize a little bit better. Using Thales' theorem, we know that this angle A and this angle S both have to be congruent because any angle on this circle with these 2 points, we know it's going to have the same angle. I think that was actually the converse of Thales' theorem. Nevertheless, So we can also conclude that these two angles are congruent. And that's all we need. So let's go ahead and write that down as well. So should I call them angle A and angle S? Because those are really the only two angles on those points. Angle A and angle S are congruent by Thales. All right. So now we have that triangle PAT. So here, let's write this down. By angle similarity, triangle PAT is similar to triangle PSB. All right. So, forgot some stuff. Let's figure out where to go from here. How about those nice similarity ratios? So, based on the similarity between these two triangles, we can conclude over here, we can declare that PT, yeah, okay, so PT right here over PB, the longest side on this triangle, is equivalent to PA over PS. Well, this just implies, if we multiply PB to get it up there, multiply PS over here, that'll give us, we can fix that, PT times PS equals PA times PB. So this is the proof of 3.6.1. This is merely Browner's second scenario where P is inside the circle, which I asked her to let me prove. Because this is pretty much the hard work in Theorem 363. The easy part now is to look at what the minor difference is between our two statements. So our theorem is supposed to tell us that PT squared equals PA times PB. And we're pretty close. Right now we have PT times PS equals PA times PB. If you'll note, we assumed by our hypothesis that P is the midpoint of TS. So what this means is that PT and PS are actually the same length. So let's go ahead and write that. By assumption, PT equals PS, allowing us to substitute here. Substitute PT for PS, giving us PT times PT equals PA PB, or PT squared equals PA times PB. And that's all she wrote.